Hi, in this video, I'll go through 3 examples of logarithmic differentiation. Now, logarithmic differentiation is an application of implicit differentiation. And implicit differentiation itself is an application of the chain rule. There are basically 2 main situations where you will need logarithmic differentiation. One is when you need to differentiate an exponential function where both the base and the exponent v are functions of x. And the other application is when your function y is a bunch of multiplications and powers and divisions. And there are so many of them that if you just use the products rule and the quotient rule, it would be too much work. In theory, any multiplication can be done with a products rule and any division can be done with a quotient rule. But when there are too many of them, it's just too much work. So logarithmic differentiation helps simplify that. But first, let's talk about the situation where the function you need to differentiate is u to the power v, where both u and v are functions of x. This is a case where you don't have a choice, you have to use logarithmic differentiation. If you only have one of them as a function of x, you don't need logarithmic differentiation. For example, if you only have the base as a function of x, whereas the exponent is a constant, then you just apply the power rule. Derivative of u to the a is a times u to a minus 1, and then applying the chain rule on top of that times the derivative of the inside, which is u prime. And that's a situation where the base is a function of x, but the exponent is a constant. Or in the case of the base is a constant and the exponent is a function of x, then just apply the exponential formula. It's ln of a times a to the u. And then the chain rule, so times u prime. So yeah, if only one of the two is a function of x, then you can use one or the other formula. It's only when both u and v are functions of x that you need the logarithmic differentiation. Let's take a look at some examples. You're given a function y is u to the v, where both u and v are functions of x. And we need y prime. Well, what you do is you take ln both sides. Then you end up with ln of y is equal to ln of u to the v. Using properties of logarithm, ln of u to v means you bring the v out in front. Then you end up with v times ln of u. That's ln of y. Now you differentiate both sides. Or you take the derivative of both sides. On the left, you have derivative of ln is 1 over the argument. So 1 over y times y prime by the chain rule. On the right-hand side, you have the products rule. And so it's v prime times ln of u plus v times ln of u prime. Now, this may be easy or hard, but it's all of the form that we can do. For example, ln of u derivative is just going to be 1 over u times u prime. And v prime is whatever v prime is. So then you can solve for y prime by multiplying both sides by y times all of this. And y is u to the v, so you substitute it back in, and you're done. So that's the general approach. Number one, take ln both sides, simplify the ln of u to the v. Number two, differentiate both sides. Number three, solve for y prime. And number four, substitute back y is equal to u to the v. So those are the four steps in using logarithmic differentiation to differentiate an exponential function. Let's do some example. This example is in every calculus book you can think of. Take the derivative of x to the x. So step 0 is to set y is equal to the exponential function u to the v. So I set y is equal to x to the x. Step 1, take ln both sides. And simplify the ln of the exponential. I mean, this x goes in front, x times ln x. Number 2, differentiate both sides using implicit differentiation. The derivative of ln is 1 over. And by the chain rule, I need to multiply by the derivative of inside, so I need to multiply by y prime. Equals. And then on this side, derivative needs the product rule. 1, derivative of x is 1, ln x, plus x times derivative of ln x, and that's 1 over x. Simplify y prime over y is equal to ln x plus, these cancel, so I have just 1 left. Number 3, solve for or isolate the y prime. And number 4, sub back whatever the y was. Y was x to the x up here. There we go. Now I have an answer. That's all in terms of x, no y in it. So that's my final answer. The preparatory step is to set y equals to the exponential function that you need. And then steps 1, 2, 3, 4. Next example, let's do sine of x to the power cosine of x prime. Step 0, let y equals to this exponential. By the way, if you're going to write this in a short form without parentheses, it's sine to the power cosine of x, similar to when you would be writing sine squared of x like that. If you write sine of x, cosine of x like this, most people would assume that you are taking the x to the power cosine x first, and then you take the sine of it. And that's not the same thing at all. So anyway, just to avoid confusion, I will write it with parentheses. Step 1, ln both sides and simplify. Ln of y is equal to ln of all of this. And when I simplify, this cosine goes in front like this. Step 2, differentiate both sides. The left side is y prime over y, 1 over y times y prime. The right side will need product rule, almost always, right? Because you're always going to have that exponent in front times the ln. Let's do it slowly. This is f, and this is g. And I need f prime g plus f g prime. F prime, The derivative of cosine is negative sign. G is the ln plus f is the cosine, and then g prime is the derivative of the ln. Derivative of ln is 1 over the inside, and then I have to times the derivative of sin x for the chain rule. So altogether, it's negative sin x times the derivative of sin x, which is cosine x. And all of this is equal to y prime over y. All right, so I'm running out of room on the right, so let me shift things over a little bit. Step 3 is to isolate y prime. Y prime is equal to y times all of this stuff. And step 4 is to sub back what y was. Y prime is equal to y. Y was the original function up here, sine x to the power cosine x. And then times all of this. And just to avoid confusion, I'm going to put parentheses around the sin x like this. Final answer. I'm not going to box it up because too many lines, just too messy. I'm just going to leave it like this. Examples 1 and 2 involve using logarithmic differentiation to differentiate a function of x to the power function of x. There's another application of logarithmic differentiation is that you can use it to make it easier when the original function has a lot of multiplication and division, and you don't want to use products rule and quotient rule too much. So logarithmic differentiation can also be used when the function y consists of too many multiplication and division. Example 3. Let's say that this is your y function, and you're asked to compute y prime. In theory, you can just multiply out the numerator and then apply the quotient rule. But that's just too much work. If you feel like doing that, by all means do. Okay, no one is stopping you. You just spend several hours doing it. Instead, you could use logarithmic differentiation instead. And the steps are almost the same as before. Step 0 is to set y equals the function. Step 1 is to ln both sides and simplify. So that's my y. I'm taking ln both sides. Ln of y is equal to ln of all of that. Now I simplify by breaking up the ln. Ln of x cubed plus 2 squared, and the squared can go in front. There's a multiplication here, so that's a plus. Ln 2x plus 7, and the fourth power can also move to the front. And then ln of the denominator there's a big division, so it becomes a minus 3 times ln of x squared plus 1. And all of that is ln of y. Step 2, same as before, differentiate both sides. And now you can see that each differentiation is just an ln. And the derivative of ln is pretty simple. 1 over y times the derivative of the inside. So on the left, the derivative is y prime over y equals 2 times 1 over x cubed plus 2 times the derivative of the inside because of the chain rule. So times the derivative of x cubed plus 2, that's 3x squared. Plus 4 times derivative of this is 1 over that. And by the chain rule times the derivative of the inside, the derivative of 2x plus 7 is a 2. Minus 3 times 1 over x squared plus 1 times the derivative of the inside, which is 2x. So you see that the derivative of ln is a whole lot easier to do than trying to take the derivative of some ungodly quotient rule. I can simplify these. Then step 3 is to isolate the y prime. Y times all of this stuff. And step 4, just as before, to substitute back the y. And y was all of this. So all of this is y, and I still need to copy all of this down. All right, here's a summary of the steps. Step 0, the preparatory step, is to set y equals to the function that we're differentiating. Step 1, take ln both sides and simplify. Step 2, differentiate both sides. Don't forget to use the chain rule and simplify as much as we can. Step 3, isolate the y prime. Now, in almost all logarithmic differentiation problems, the derivative on the left side is going to be y prime over y. So to isolate y prime, usually all you need to do is multiply both sides by y. And then you substitute back the y for whatever the function was at step 0. All right? Hope that helps. Any questions? Ask in the comments. Like, share, and subscribe for more contents. And thanks for watching. Bye.